So there are your double angle identities. There is a single double angle identity for sine. Sine of 2 theta equals 2 sine theta cos theta. Or on your formula sheet, they have alphas. Tan of 2 theta equals 2 tan theta over 1 minus tan squared of theta. And then cos of 2 theta, or 2 alpha, whatever angle you want to decide to use, has 3 different variations. And we're going to see at least one example today where you have to make a decision as to which of those 3 is your best option to work with. Any one of the 3 will always work, but one of them is the quickest path to your destination, usually. So cos of 2 alpha equals cos squared alpha minus sine squared alpha, not to be confused with the Pythagorean identity at the bottom of the screen here where it says sine squared theta plus cos squared theta equals 1. Then also for cos of 2 theta, we have 2 cos squared theta minus 1, and we also have 1 minus 2 sine squared theta, or alpha. I know I'm being very inconsistent here. I'm switching back and forth between alpha and theta, but they, as long as you're using the same angle on each side, then it works. So taking a look at your work here on page 14 of the handout, questions 1 to 4, does anybody have any questions you would like me to go over here? Ian? 2C? So use a double angle identity to simplify this expression. You should recognize that forgetting for a second here, Ian, about the pi over 12. What we are seeing here visually is cos squared of some argument minus sine squared of some argument, right? The argument is the thing you're operating on in mathematics. So root 12 has an argument of 12. 7 squared has an argument of 7. Cosine squared of pi over 12 has an argument of pi over 12. But forgetting about what the specifics of the argument are, cos squared of the argument minus sine squared of the argument is equal to cosine of 2 times the argument.
Are we doing 2C?
Oh, I thought you said B. No, don't apologize. I must have misheard you. That's my fault. Does anybody want me to continue with B? Okay. Sorry. C. So what we are looking at in C is sine of an argument times cosine of an argument. But unfortunately, I don't have an identity on my formula sheet that says sine argument, cosine argument equals something. I do, however, have this identity on my formula sheet. I have sine of 2 alpha equals 2 sine alpha cosine alpha. And what we have here is part of what we have here. So what we're going to do is take that identity I've written down on the left and arrange it so that I do have sine argument, cosine argument. And what I'm going to get is 1/2 sine of 2x equals, well, I better be careful today. I'm sloppy with my angles. Alpha equals sine alpha cosine alpha. So what I'm doing is I'm customizing the identity on the formula sheet to match what I have here. So that means that this is equal to 1/2 times the sine of 2 times that argument. Does that make sense? Okay. Bottom line here is that for C, I can write sine of 5 pi over 12 cosine of 5 pi over 12 is equal to 1/2 times sine of 2 times 5 pi over 12. Good. And this gives us 1/2 times sine of 5 pi over 6, because 2 over 12 reduces to 1 over 6. And we know what sine of 5 pi over 6 is, or we should be able to figure it out with a little bit of thought. 5 pi over 6 is in quadrant 2 with a reference angle of 30 degrees, or pi over 6 radians. When you start looking at the unit circle, the coordinates of this point are negative root 3 over 2, comma 1/2. Sine is the y coordinate, which is 1/2. So this becomes 1/2. The sine of 5 pi over 6 is 1/2. So the answer is 1/4. Yep.
Why did you multiply what I got? Sorry, I should start off.
This is a tricky one. We see in here, Shesmaida, a cos squared minus sine squared, right? And that's kind of familiar to us because cos squared of an angle, I'm going to go with theta, minus sine squared of theta gives us cosine of 2 theta. Right? But I don't have up here cos squared minus sine squared. I have a times cos squared of an angle minus a times sine squared of an angle, but I can factor that a out. And if I factor a out, I'm going to have cos squared of pi over 8 minus sine squared of pi over 8 equals 4 root 2. Is that okay? Okay, but now we can use this identity for cos squared minus sine squared. It's going to be cos of 2 times that angle of pi over 8. And this is equal to 4 root 2. Now we're doing this because we're after a. And at this point in time, what you can do is you can calculate what this trigonometric ratio has for a value. Because 2 pi over 8 is pi over 4. It simplifies to pi over 4. So we get a times cosine of pi over 4 equals 4 root 2. And again, we're trying to figure out what a is. What is the cosine of pi over 4? Well, pi over 4 on the unit circle has coordinates of root 2 over 2, comma root 2 over 2. So the cosine is root 2 over 2. So we end up with a root 2 over 2 equals 4 root 2. Now what we just have is an equation where you have to solve for a. Well, I would divide both sides. I don't know that we really need to show this. I would divide both sides by root 2. And then I'm left with a over 2 equals 4, so I can multiply both sides by 2 and get a is equal to 4. A is equal to 8. Does that make sense? Okay. Other questions? Go ahead, Marcel. Number 3? Certainly. So we're asked to determine this expression. Now, the top of this expression is going to be cosine of 2 times 3 halves x. Do you see how I'm able to do that? Because of the double angle identity for cosine. Cos squared minus sine squared equals cos of 2 times the angle. Now, we've already had this discussion here that this is not quite the sine of 2x or 2 theta deal. But if you write sine of 2 theta equals 2 sine theta cos theta, we can engineer this so that the identity matches the denominator there. See what I'm getting at? Okay. So if I divide both sides of this identity by 2, I get 1/2 sine of 2 theta, which means on the bottom of this, we're going to have 1/2 sine of whatever 2 times 3/2 x is. And when we take 2 times 3/2 x, the 2's cancel. So we're left with 3x. What we have now is cosine of 3x over 1/2 sine of 3x. This is cotan of 3x. And by the way, this is also something that we would probably multiply top and bottom by 2 to get rid of that fraction of a half. So we really end up with 2 cos 3x over sine 3x, which is 2 cotan 3x. Is that okay? Okay. Other questions? Okay, we're going to move on today and look at proofs, trigonometric proofs, and we're going to be spending today and tomorrow on this. So we're going to be working on this today, doing the lesson today and getting started on practice, and then tomorrow during our seminar and tomorrow in our regular class, we're going to continue to practice trigonometric proofs. I've already demonstrated to you in one lesson, one example where we had a proof. So this isn't really anything new. The thing that's going to be different is the complexity is going to be kicked up a notch, because when we first did a proof, everybody, all we knew about were Pythagorean identities, quotient identities, and reciprocal identities. Now we know all of these identities. So we're going to be proving trigonometric identities and occasionally verifying trigonometric identities. First of all, I want to talk about non-permissible values for rotation angles and trigonometric ratios. Ultimately, you get a non-permissible value because you're dividing by 0 somewhere. And all of the trigonometric ratios are defined in terms of x, y, and r. So, for example, tangent is y over x. X can never be 0. If x is 0, then you're dividing by 0, it's not permissible. So any place you have a rotation angle where x is 0, tangent will not be defined. There will be a non-permissible value there. Keep that in mind as we go through these examples. As well, please remember, don't simplify the expressions to find non-permissible values. Those of you that are in calculus, and there's a couple of you here, few of you, you know that non-permissible values are found before you cancel. You cannot cancel things and then work on non-permissible values. So let's take a look at the first example. We are asked to we are asked first of all to determine non-permissible values for this equation. So what we're going to do is we're going to write this in terms of sine and cosine. So tangent is sine of x over cosine of x. And then we're multiplying by cosine of x. And we're dividing by cosecant of x, which is 1 over sine of x. And this is equal to 1 minus cosine squared of x. So remember, you cannot divide by 0. What does this mean? It means that this thing cannot be 0. That cannot be 0, because if that is 0, then sine of x over cos x is undefined. You cannot divide by 0. This cannot be equal to 0 because it's a denominator. Sine of x is a denominator. It's a mini denominator, but it's a denominator. And lastly, this cannot be 0. Those three highlighted things are all, each of them, denominators. So that means that this 1 over sine of x is not allowed to be 0. It means that cosine of x is not allowed to be 0, and it means that sine of x is not allowed to be 0. So let's start at the bottom here with sine of x. Where is sine of a rotation angle 0? I want everybody to think about that. So when you look at the unit circle, and I think we have to go with the unit circle approach here. I don't think you want to be trying to solve an equation like sine of x equals 0 by finding a reference angle. It gets too cluttered and confusing. Sine of x is 0 in terms of the unit circle. It's a little sloppy unit circle, but sine of x is 0 here and here. And that means that we have a non-permissible value for x, that x cannot be equal to multiples of pi. 0, pi, 2 pi, negative 2 pi, negative 3 pi. Where is cosine of x equal to 0? Well, cosine of x is equal to 0 here and here. And that means that x is as well not allowed to be pi over 2 plus multiples of pi. Any questions with those two sets of non-permissible values so far? Okay. This never happens. You cannot have a fraction like 1 over something ever become 0, because the only way a fraction can be 0 is if the top of the fraction is 0. You cannot have 1 over something equal to 0. So these are our non-permissible values. We can combine these and just say that x is not allowed to be multiples of pi over 2. Because if you look at that circle I've drawn, if you look at that circle I've drawn, this is 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, negative pi over 2, negative 2 pi over 2, etc. So those are the non-permissible values. So any questions with A and finding the non-permissible values? This thing that I have on the left of highlighting all the denominators is kind of important. By the way, you'll notice I didn't deal with the right-hand side because there are no denominators in the right-hand side. There aren't any denominators on the right-hand side that have x in them, or trigonometric ratios. All right, let's do the proof now. And, I guess we still have one more thing to do. Let's verify this. Let's put into our calculator for y1, the left-hand side, and for y2, the right-hand side. And you'll want to follow along very carefully because entering the left-hand side is tricky. I have to enter tan x times cos x, and then I have to divide by cosecant. Well, we have to deal with something here, and it's that your calculator doesn't have a cosecant key. So I need to divide by 1 over sine x, but I need to have that in brackets. If you divide by, without brackets, 1 and then divide by sine of x, that's not the same as dividing by 1 over sine x. So I have to now go 1 divided by sine x. Close the brackets on both of those. And then we're going to enter for y2 1 minus cos of x quantity squared. And again, that squared to some of you doesn't look like it's in the right place, but it is. That is squaring cosine of x. Double check the entries. We're not going to do a graph here because, and we can work around it, but if the graphs are identical, we'll just see the first one graphed and then we won't see anything else because the other one will be on top. We're going to go to our table, and my table happens to have some numbers in it already. I was doing some stuff in a calculus class yesterday, but I suppose what we could do is put our calculator into degrees, set up our table to start at 0 and go up by 15 automatically. It doesn't really matter, but 15 multiples of 15 will hit 30 and 45 and 90, etc. So when you look at your table, y1 and y2 are always equal. See, they're equal here, they're equal here, they're equal here. They're not always equal, but when they're not equal, it's because there's a non-permissible value. And an identity is something that's true anywhere other than non-permissible values. All right, now we'll do the proof. And by the way, you will notice in this lesson that for each example we do, I direct you to a different example that's similar in your textbook. Okay, so we're going to prove this. And I want to point out to you, if you look at your pink sheet, that I've given you all of these suggestions for simplifying rational expressions. Now, when you're proving an identity, you want to turn the left side into the right side, or turn the right side into the left side, or work on them both separate from one another so they become the same thing. But ultimately, everybody, that means you have to simplify them. You have to simplify the left side and simplify the right side, and hopefully they come together. If you turn that sheet over, the other side says when proving a trigonometric identity, you're going to do all these things that we've been working on, but you're also going to keep your eyes on the prize. If you're trying to turn the right side into the left side, then you have to continually be looking at the left side because that's your goal, or vice versa. All right. So, when I look at this, and I look at, say, we'll do the left side first. I see tangent and I see cosecant. One of the things that I've taught you that I hope you remember is it's always useful to rewrite everything in terms of sine and cosine. And I don't know if you remember this. I think you might. When you're doing a proof and you use an identity, you need to name the identity that's being used. So I used tangent equals sine over cosine. So I used a quotient identity. And I also used 1 over sine equals cosecant. So I used a reciprocal identity. And I do need to name them both. So this is written because there's a quotient identity. This is written because there's a reciprocal identity. Any questions with that first step? My advice to you is algebraically don't try to do too much at once. Okay? Don't try to do multiple steps at once. So there's a couple of things that need to happen here. One is the cosine cancels on the top and the denominator in the top. The other is I got to get rid of that denominator in the bottom. Just rewrite the whole thing and then get rid of the denominator in the bottom. So I now have on the top sine of x over 1 over sine of x. Now what I'm going to do is multiply the top and the bottom by sine of x. You need to explain or describe or name the identities if you use an identity, but algebra does not need to be explained. You don't need to explain what's happening here. What happens though, and it's by design, is the signs cancel and you're left with sine squared of x. Now let me bring this down. How many of you see these are equal? I hope everybody. But we're not done the proof. Whatever we have on the bottom of each column in the two-column proof has to be exactly the same. So I would just write 1 minus sine squared, 1 minus cos squared of x here, and write Pythagorean identity. Could I have left the left side as sine squared of x and then written the right side as sine squared of x? Sure. But I'm just thinking, since we were working on the left, why don't we just continue and roll with it on the left? Now, we were also asked, no, we weren't asked. So that's it. Any questions with, now we can write left side equals right side. Any questions with number 1? I think some advice I would give you is, don't try to do too much at once and just be organized. I know some of you do stuff and you draw arrows up here and you write stuff and then you put an arrow down here. A two-column proof has stuff that you're just working down on each side, nice and lined up. Let's try another one. Prove this identity. Sine of 2x over cos of 2x plus 1 equals tan x. And I want to, and then we also have to do non-permissible values. I want to give you some reassurance here. These things look really difficult, right? They do. I get it. But if you just sit there at your desk and stare at it, there's not gonna be some massive light bulb that goes off in your head and goes, oh, I see exactly how to do it. You have to try. You have to start using identities to rewrite things. So when I take a look at the left side, I see sine of 2x. There's only one thing I can do with sine of 2x, right? When you look at your formula sheet, sine of 2x, which is at the top of the screen right now, is 2 sine of x cos x. Well, let's do that. So I'm going to have 2 sine of x cos of x on the top. And that's a double angle identity. Now, I also have on the bottom cos of 2x plus 1. So I need to replace cos of 2x with something. And I'm going to write down the 3 identities. You don't need to write them down. You can just look at your formula sheet. But here are the 3 identities, and I'm going to erase them in a bit. Cosine of 2x is cosine squared of x minus sine squared of x. That's a fact. Cosine of 2x is 1 minus sine squared of x. No, it isn't. It's 1 minus 2 sine squared of x. And cos of 2x, another fact, is that it's equal to 2 cos squared of x minus 1. Did I get them right? My question to you is, in here, we need to put cos of 2x. My question is, are we going to put this? Are we going to put this? or are we going to put this? And neither answer is wrong, but one of the answers will take us to the proof quicker. So I want you to roll that around in your head and ask yourself, which of those three is going to be the most useful when we put it in?
Couldn't you add both sides? Or could you add one to both sides of the yellow one?
Okay, so yes, you could. And I'm going to come back to that because you're thinking of a substitution to make it work. But I want to stick with my question right now. I know what you're saying, okay? You're going to make an identity fit with what's there, right? Okay, that's fine. But I want to approach it in this way. Which of these three substitutions, when I put it in here, will simplify quicker or easier? Do I? The yellow one. Because I'm going to have 2 cosine squared of x minus 1, but then I'm adding 1 and they go away. Now, I am going to address what you said, but I want to finish this thought first. So what this becomes, and by the way, that substitution to get here is still a double angle identity. You don't need to write that double angle identity twice in green. So what we end up with is 2 sine of x cos of x over 2 cosine squared of x. And I don't think most people need me to write this way, but I'm going to. Because I really think this idea of canceling only when you have a common factor to cancel is important. So what's happening here is, since cos of x is a factor on the top and the bottom, you can cancel. Since 2 is a factor of the top and the bottom, you can cancel. And you're left with sine x over cos x. So we can write tan x because of a quotient identity. And we can say left side equals right side. So now we still have the non-permissible values, and I'll get to that. But Marcel, I want to address what you said. What Marcel said, and the answer to the question is yes, you can do this, is we were at the stage where we had 2 sine x cos x over cos 2x minus 1. And we also have this identity that says cos of 2x equals (1 minus 2 sine squared x). Pardon me?
I think the denominator was +1.
Was it +1? Okay, thank you. And I guess that's not the identity we're going to use. We're going to use cos 2x equals 2 cos squared x minus 1. And what Marcel was saying is, can I make this identity that I've written on the right match what's in the denominator? Right? So he adds 1 to both sides and gets cos of 2x plus 1 equals 2 cos squared x. So this is the entire denominator, and he's going to replace it with 2 cos squared x. And I'm going to say that's right. But, and there's nothing wrong with it, but it's not always a good move, because this number might be 4 next time. And you can't make that identity fit that unless you write it as cos of 2x plus 1 plus 3. But yeah, as long as you're following the rules of algebra and substitution is legit and rearranging is legit, it's good. Okay? We still have to do the non-permissible values. So when we look at, I don't want to do non-permissible values for this. Let's not do it for this. Okay? Because we need to know something from the final lesson in this unit for this non-permissible values. So we won't worry about it. Number 3. So I'm just making a note for myself about that. Number 3, and again, there's something that's similar in your textbook. Prove that this equation is true, and then we're going to find the non-permissible values. So there's the left side and there's the right side. There's something in this question, I believe, that's very specific. It's not something that's on that pink sheet. But before we do this, does what I'm about to say kind of make sense? Think about it after I say it, and then we'll talk about it. If you're trying to make both sides equal to each other, and one is more complicated, isn't it reasonable to try to take the complicated one and simplify it into the simpler one, rather than to take the simpler side and try to somehow make it more complicated? I think that rings true, doesn't it? So just looking at this visually, the right-hand side is more complicated. So what are some things we could do? I know that what most of you would do first is to write everything in terms of sine and cosine. So I can write the secant as 1 over cosine, and then I have minus sine of x times 1 over cosine. Look at how neat and lined up everything is. I think that's important. Not because somebody's going to be marking your work and they're going to be impressed by it, so much as because it's easier for you to follow your work when you do it. And then we have over cosine. I didn't really leave myself a lot of room here. I think you have more room. This is a reciprocal identity. That we're using. So all I've done is I've rewritten it, and every place I see a secant, I've written 1 over cosine. Does that look okay? In other words, any questions with that? Okay. Now what I'm going to have to do is, because I have a complex fraction, and I'm just going to ask for my purposes for next time I print this out. Do you still have enough room on the right-hand side? Okay. We're going to now multiply the top and the bottom by cosine of x, because we would like to get rid of this and this, right? This is the quickest, most direct way of simplifying a complex fraction. When I multiply the 1 over cos x by the cos x, I get 1. And when I multiply the sine x times 1 over cos x, which is the second term, when I multiply that by cos x, the cos x cancels with the cos x, and I'm left with sine x over cosine squared of x. Any questions there? Yeah.
How come before you multiply top and bottom by cos x, how come you don't just say that, well, sine x times 1 over cos x is just sine over cos x? And then if you have 1 subtract sine x, because they're both over cos x on the top, you have negative sine over cos x.
Let's talk about that. What Ian is saying, I believe, is if I take a look at the top of that expression, So let me just go to a new page with this. So what Ian is saying is, I have a common denominator on the top. And I have 1 over cos x minus sine x over cos x over cos x over cos squared of x. And I'm going to just begin with a statement that it's the same kind of thing that I told Marcel. As long as you're doing algebra properly, you can get to the answer here. Okay? And so far, this is golden. It's pristine. There's nothing wrong with your logic. And your next statement, I think you said, so this is 1 minus sine x all over cos x, cos squared of x. No, all over cos x, all over cos squared of x is correct.
Not cos squared x on the bottom just yet.
Right, because you're not multiplying top and bottom by. Okay. So you get this. Now what? Now I believe you said this is 1 minus sine x. Because in your mind, the cos x cancels with the cos x. And that's the flaw. Because if I ask you what 1/4 divided by 4 is, right? 1/4 is 0.25, is it not? Take your calculator and take 0.25 divided by 4. You do not get 1. You cannot do this. That's not allowed. That's not the way fractions work. And maybe I can illustrate this by saying that's why we would never write something like this, where it's ambiguous where the fraction is. If this is the fraction, and you say I'm going to cancel a 4, then you're claiming that 4 is a factor of the top and the bottom and I can cancel it. It isn't. If you want to stay with this and simplify this, then you have to multiply the top and the bottom by cos of x. Yes, and that's the point. You're going to get 1 minus sine x over cos squared of x. So be very careful with your thinking of canceling stuff. The other option here is you could take 1 minus sine of x. I don't like this because it's too limited, but it would work here. You could take the top of that fraction, and since the bottom is cos x over 1 and you're dividing by cos x over 1, rules of fractions say you multiply by the reciprocal of the fraction you're dividing by, and you get 1 minus sine x over cos squared of x. But again, I don't recommend that. I recommend always, so when you have a complex fraction, Ian, like we do here, and this is actually just cos x, isn't it? When you have a complex fraction, do not think common denominators to build it. Think, how do I get rid of the mini denominators by multiplication? Is that helpful? Okay. So, now, how do we turn this on the right-hand side into this on the left-hand side? And I've actually talked about this next little bit of business, which isn't really on your formula sheet. It kind of is, not formula sheet. The idea isn't really on this pink sheet, but it kind of is. Does anybody have an idea of where to go here? Arden? Perfect. Do something that we would normally not do. Normally, if you had 1 minus sine squared of x, you'd turn it into cos squared. You would normally do that. But the reason why Arden is saying we're going to replace cos squared with 1 minus sine squared, and before we forget, we'd better write Pythagorean theorem or Pythagorean identity, is because I believe Arden is looking one step further down the road, and he knows that he can do something with 1 minus sine squared. What can you do with 1 minus sine squared? It's a difference of squares. And one of those factors, when we factor 1 minus sine squared, will be 1 plus sine of x. The other will be 1 minus sine of x. And we have 1 minus sine of x on the top, so it cancels. And we're left with 1 on the top and sine of x plus 1, while we're left with, I better be very clear here, we're left with on the right-hand side 1 over 1 plus sine of x. Well, that's the same as 1 over sine of x plus 1. It doesn't, you don't have to rewrite it with those two terms switched. So now we can say left side equals right side. What about non-permissible values? Well, we have here 1 over sine x plus 1. And then over here, we have, I'll risk it. Nope. Over here, we have what I'm going to highlight in yellow. That's the right-hand side. So we're looking before we start multiplying. So we have a denominator of sine of x plus 1. You can't divide by 0, so sine of x plus 1 cannot be 0. So I think you're going to have room in the bottom right corner of your handout. We can write there that sine of x plus 1 cannot equal 0. Because there's a denominator of sine of x plus 1. We also have a denominator of cos of x, both here on the bottom and here on the bottom of the top. So that means cos of x cannot equal 0. Well, this first little equation, or non-equation because it's not equal to, translates to sine of x is not equal to negative 1. So where is sine of x negative 1? Sine of x is negative 1 on my lopsided unit circle here. Where is cosine of x equal to 0? Here and here. So how do we describe all of these? Well, we can say that it's pi over 2 plus or minus multiples of pi. I don't think that would be what we would write for an answer. I'm just indicating on my diagram why we can write for non-permissible values x is not equal to pi over 2 plus multiples of pi. I think I forgot to do this in the earlier question. I think I forgot to write n as an integer. We need to do that, right?
You didn't do the non-permissible values for the previous question.
I know, because I said we weren't going to do them.
Well, I'm just saying that
The previous one that we did non-permissible values for, I didn't put n as an element of the integer. Number 7. Okay, we have one last example to go. And when you look at this, this looks like a beast, but it's not. This is literally the case where, well, it's figuratively the case that you're standing on the road and it's like very scary. And you take 2 steps and the sun comes out when you pass that hill. And the birds are chirping and there's an ice cream stand and everything is beautiful. Okay? We have to have the confidence in ourselves to start walking. You can't panic and just look at it and go, oh, I don't know what to do. So we want to prove this. Well, look, there's only one thing you can really do on the left-hand side with identities, and that's to rewrite sine of 2x as the equivalent side of the identity that sine of 2x is equal to. It's equal to 2 sine x cos x, and then minus cos x, and this is over to 4 sine squared x minus 1. And that is a double angle identity. And we're kind of at an impasse now. We can't see the ice cream stand yet, but we can hear the bell and the music. We know that there's something around the corner. One of the most important things on this sheet that I've given you is factoring. Because after all, when you take a look at this expression on the left, it's a rational expression. And I don't mean to bring up what was a difficult unit in Math 20 and bring back bad memories, but rational expressions are always worked on by factoring everything first. Now, we used identities here to clean it up, but I have a common factor of cos of x on the top. So I can factor out a cos of x and have left 2 sine x minus 1. So when I take a look at these 2 terms, I hope the highlighting helps here. When I take a look at these 2 terms, this term minus this term, there is a common factor of cos x. So that's what I'm factoring out. And I'm left with whatever's left over, 2 sine x minus 1. Does the bottom factor? Can I factor 4 sine squared x minus 1? Yes, and as soon as you see that it's a difference of squares, you're probably going to see what's going to happen when we write it in factored form. This will factor on the bottom into 2 sine x plus 1 and 2 sine x minus 1. Oh, that's a thing of beauty. Those 2 things cancel. So we're left with, on the left-hand side, something that's really not that complicated. But, and I talked about this earlier, I don't think, everybody, that you're going to try to turn this into that, right? I think the idea here is you get to this stage, and my road analogy is quickly falling apart, but you get to this stage on the left-hand side, and you go, I'm just going to leave that alone, and I'm going to work on the right-hand side. And on the right-hand side, I can factor out of the 2 terms on the top, sine squared of x cos x and cos cubed of x, I can factor out cos of x. And I want to ask you this question. How many of you see we'll pretty much be done? Because if I factor cos x out, I will have left sine squared of x plus cos squared of x. And this is over 2 sine x cos x. How many of you now see that we're pretty much done? Then maybe you didn't a minute ago. Hopefully everybody is recognizing that this is 1 because of the Pythagorean theorem, so we can write cosine of x over 2 sine x. I don't know why I wrote 2 sine x cos x. It's 2 sine x plus 1. I apologize. Over 2 sine x and then plus 1, and you can see that the left side is equal to the right side. So what really, when you take a look at the big picture here, everybody, meaning the whole question, and you look at what we did, we didn't really do a lot of work. But when you look at the original question, prove that, it looks complicated. I'm not trying to say that this is easy, right? I'm not trying to say this is easy. I'm trying to say you can do it, but it requires you to continually be referring to the steps that I recommend, to have your formula sheet in front of you, and to try. So as you're working through these, your pencils should be moving, and then your eraser should be moving, because you're going to make mistakes invariably. Or it isn't that you make a mistake, you took the wrong path, right? You stumbled into a den of bears, okay? So that's not where you want to be. You want to go back to the beginning and find that meadow with kittens and bunnies in it, okay? Any questions with that example? Marcel, do you have a question? No? So we're in the textbook now for these proofs, 1 to 8, 10 to 13, 15 to 18 on page 314. I want to point out something to you. When we learned about Pythagorean reciprocal and quotient identities, I gave you a list of extra practice problems, but some of the ones in the section in your handout were not included because they were proofs. The same thing with sum and difference identities. The same thing with double angle identities. So you can find extra practice proofs on these pages. The more of this stuff you do, the better you will get at it. So get to work on that. I'll be around to just check on you and help you out in a few minutes.